Hello, everyone. I see some people are starting to join the webinar now. I will give everyone a couple minutes to join before we get started. While we wait for more people to join, I'll give everyone another minute or two, but feel free to drop into the chat where you're calling in from today. I'm calling in from Canada in Whistler, British Columbia. Dan, where are you calling in from today?
Houston, Texas.
Awesome. What about you, Juan?
Cleveland, Ohio.
Awesome. Christine?
Huntsville, Alabama.
Awesome. All over the country. Right. It looks like we have quite a few people in here now, so I think we can get started. First things first, this webinar is being recorded, so there's no need to take notes or anything throughout this. It will be posted on the challenge page. So you can just sit back, enjoy, and take everything in that you can. We'll start off with some introductions. My name is Natalie. I am a challenge manager at HeroX. So I help all of our clients launch their challenges and support them through the process of running them. So this is probably about my maybe second or third NASA challenge, and I've got to work with a load of other great clients from the US government and all over the world. And then I will pass it over to the NASA team to do some introductions as well. So Dan, why don't you kick us off?
Well, hello, everyone. It's a pleasure to be here, and NASA certainly thanks all of you for considering submitting to this challenge. I've been at I'm a scientist and project manager at Johnson Space Center, and I've been here about 30 years. And this challenge addresses one of the technologies that we're developing for which we'd like to get input from all of you. Chris?
Hey, this is Chris. I have been at Marshall Space Flight Center for about 14 years, working in carbon dioxide recovery and removal. And so I'm kind of excited to be here for this. Thanks.
Juan, why don't you give us one?
Yeah, and I'm Juan Agui. I'm with the NASA Glenn Research Center in Cleveland, Ohio. I've been here for about 23 years, and I've worked multiple projects throughout the years. I started it actually in the microgravity division, supporting the ISS experiments. And then more recently, I've been involved with aerosols and air and gas filtration, and been working on the life support systems projects for quite a bit, developing technologies for future missions, including this type of technology where we're interested in mitigating the effects of carbon dust in this ecosystem.
Wonderful. Thank you. We're excited to have you all here. So how the webinar is going to work today, I am going to pass it over shortly to the challenge team, all of these three from NASA, and they're going to give you a presentation about the challenge. So nothing there should be a major surprise. It's mostly what's on the challenge page, but we find it helpful for innovators to hear straight from the challenge team about what they're looking for and why they're running this challenge. And then we're going to go into a Q&A session. So we've already received a few questions from the audience, and all of you joining today will also have an opportunity to ask questions if you have them. So if you do have questions come up at any point during this webinar about the challenge, you can drop them into the Q&A box. If you're calling in from the Zoom app, you should see a Q&A button along the bottom of your screen. You can click that and enter your question. Please don't drop them into the chat just because there might be other things going on in the chat and we might miss them. But otherwise, if you have any issues come up, you can use that chat box if you can't hear someone or something like that. Like I said, this is being recorded, so no need to take notes. Just pay attention and take everything in. Awesome. So at this point, I will pass it over to Dan to discuss the challenge, and I'll be sharing his slides here.
Thanks so much, Natalie. This first opening title slide does actually show our names and our affiliations for you to see that. And I think these slides will be also made available by Natalie on somewhere on the HeroX webpage.
Yes, they will be.
Yeah, good. Okay. So if we can go to the next slide. Okay. So first thing I would like to kind of do is give you a background, which really goes beyond the challenge specifically, to kind of give you a little bit of a history of what we're working on, why we're working on it, which is kind of a bigger picture. And then the specific technology that we'd like to get input on for, basically it's a process technology in which we'd like to have carbon particulate separated from the gas stream internal to this device. Then talk a little bit more about the particle partition challenge, and I think maybe also to cover the judging criteria, and then we'll go into question and answers. Next slide, please. So oxygen is a very critical gas and consumable in space flight. Basically, it helps, for instance, human respiration, breathing. We need it. It's a critical item, and it's a consumable. We breathe it in and we exhale carbon dioxide. So we need to constantly provide it for crew. The longer the crew's in space, the more oxygen we need. On the space station, oxygen is provided either as a compressed gas or most likely by the electrolysis of water that's stored on board, and that's either brought up from the Earth or recycled water in flight. The longer and longer emission, the more oxygen we have to bring. This is a huge mass weight that penalizes us in terms of the launch vehicle launch mass. We need extra propellant in order to launch it. So if we can recycle oxygen in flight, it's desirable. And so we're looking at carbon dioxide, the ability for us to basically crack it and recover oxygen from it. And it'll really enable long duration stays in space away from low Earth orbits, such as station. We're really close to Earth, so we can bring up things. But once we get away from Earth, either at the moon or to Mars, it's more desirable to be able to recycle and recycle more completely. Next slide. Currently on the space station, we have used and tested a form of oxygen recovery hardware called the Sabatier. And there's also one that ESA is evaluating. It's part of an advanced closed loop system. The NASA Sabatier currently has been returned to Earth for refurbishing and upgrading, then it'll be brought back. But it reacts carbon dioxide and hydrogen and forms methane and water. And that water is what we use for getting oxygen through electrolysis, as I mentioned earlier. The one issue with this, though, is if you look at some of the hydrogen that's required in the reaction, it goes to the formation of methane, which is effectively something we vent and cannot use in flight, although there are some methane engines that are out there. So if we can have a reaction that's much more efficient, in which we don't need hydrogen, we can actually react, so we don't need as much hydrogen. We can react, we'll have more available to react with carbon dioxide. As it turns out, there's only about enough hydrogen available in flight, which comes from the oxygen generating system, the OGA, which is an electrolyzer, to react about half of the carbon dioxide and recover half the oxygen from it. So if we're not wasteful with hydrogen, we can hopefully get 100% oxygen from the available carbon dioxide. So in the next slide, I talk about our target technology. which is the Bosch technology. And there are various forms of this that NASA's looked at over time. The reaction for Bosch reacts hydrogen and carbon dioxide. The net reaction produces solid carbon and water. There are a bunch of intermediate reactions, one reverse water gas shift. There's a carbon monoxide hydrogenation reaction and a boudoir reaction, but all of these add up to effectively complete utilization of hydrogen towards the recovery of oxygen. And this is the technology of interest to us. There's a couple different types and manifestations of the system. We are focusing right now on the third one, but I'll talk a little bit about some other ones on the next slide. So we were originally considering Bosch for the International Space Station, although eventually the Sabatier did win out in the sort of the trade studies, and partly because the Bosch did not trade off. It had really high consumption of consumables. If you look at the reactors on the left and the one on the right, you see these cylindrical shapes, which represent the Bosch reactor. The rest is sort of the control system for it. But these reactors were packed with either a glass wool or some kind of a ceramic wool in which was embedded catalyst, and in most of these cases it was either nickel or iron catalyst. And as the reaction occurred, the carbon formed, the wool would trap the carbon, and eventually this reactor would get so dense, filled with carbon, that the pressure would increase in it. There'd be a pressure drop. It would effectively, the pore space would be exhausted, and though these reactors were not renewable or regenerable, basically we had to put a new reactor in place that was loaded with the wool and the catalyst, and that was a huge expense from a consumable point of view. We had to have a lot of these cylinders on board, and when you compared the mass of these cylinders to the mass of oxygen recovered, it was prohibitive to really bring these technologies. So we're looking at a new design. Next slide, please. So the concept we're looking at, and which is particularly focused of the challenge, is called the continuous Bosch reactor. And Natalie, if you could move your cursor around sort of the gas loop, the green going down to the condenser, across recirculating stream up through the reactor. The gases in this reactor design go clockwise. Hydrogen and carbon dioxide are fed up through the bottom of the reactor. They're heated to the 600 to 700 degrees centigrade sort of range of temperature. The hot catalyst engages the reaction, but it's only about 20 to 30% efficient. So there's a lot of unspent reactants that are recycled in this, and every time you recycle through the reactor, you get more and more closure or reactant of those gases. But it's a continuous process, and as carbon is formed, the intent was the carbon would go down a chute into a collection reservoir, which would have some easy means to be able to regularly remove that carbon and safely, so that carbon dust didn't affect people in terms of getting into the cabin air. And then at the top of the reactor, we had a filter. In this case, it's a frit filter that allowed gases to go through but held back the carbon. Now, our problem with this was that this frit filter would either get clogged in terms of its pore spaces filled with carbon, or a bed of carbon would build up, a cake of carbon against the filter, basically shutting down flow and necessitating either cleanup or just rendering this idea a new idea for how to filter out that carbon to keep it from going in that gas loop. A particular concern was the condenser, which is where we collect the water from this process, which in turn is used for oxygen a source of oxygen, we didn't want to gum up that reactor with carbon. And so it's very important to keep carbon from getting into that condenser, at least if the condenser is not designed to accommodate particulates. Hopefully I covered that sufficiently. Next slide. So what we would like the group of challenge participants to do is to look at how we could better separate the carbon from this recirculating gas stream and be able to collect it in a safe way and in a way which we can remove that carbon while the reaction is still going. So some means to be able to collect the carbon safely, as well as separate the carbon from this recirculating gas stream. In a typical day, approximately 250 grams of carbon is produced per crew member, or for a crew of 4, which we are targeting our system for, about 1 kilogram of particulate carbon would be produced each day. The condenser operates actually probably at about 5 C or so, and then that's basically very chilled fluid runs through a condenser. So we have a hot zone on the outlet of the reactor, and it's cold by the condenser. What our thought here is that if there could be a separator, it's either going to be in the hot zone, so where the gas phases occur, or possibly have it in the cool zone where water is formed, but with some design that accommodates not only the collection of carbon, but an easy separation from the water. The flow rates through this system of gases are on the order of 20 to 50 liters per minute. So pretty high velocity flow goes through there. If you go back to the prior slide, one can see in the center, there's a picture that shows some fluidization of carbon from a bed where when carbon's generated, some of the heavier carbon stays low in the reactor, at least if it's in a partial gravity context. And as that carbon builds up, our original thought was it would go down a chute, which you can see in the schematic on the right. But some of that the very fine carbon is entrained in the gas stream, and is what is then, at least in this context, hits that FRIT filter. So what can we replace that filter with? Would be a question. A different type of separation system is of interest. Next slide. And then maybe the next one. So just some information about the carbon. There's pictures on the right are enlarged, showing kind of the grain, the size. It's kind of, it's kind of sort of semi-spherical. It's not long chains or really flat, like it's not really graphene. And you can see that they're from the graph that there's a lot of carbon between 10 and maybe 500 or so microns in diameter, but this is a graph that's volume, which is also related to mass, but because a lot of the fines don't have a lot of mass, you don't really see them detected here, but there is probably a number of fine particles that are in the 0.1 to 10 micron range that just aren't well depicted. I have a little vial here of carbon, and I don't know let's see how easy it is for you to see it. You're going to make me larger there for people to see? I don't know.
Continue. There you go.
But it's pretty fine, and there is some that tends to settle much more slowly than the rest does. So, okay. You can go back to the slides, maybe. Okay, next slide. So just going through some of the performance criteria. Ideally, we would like all of the carbon to be separated and removed from the flow loop. Ultimately, we think there might be downstream like a little HEPA filter that maybe gets any residual, a couple percent, that if the main system isn't effective. But hopefully that won't be so much that it would be high cost to keep having to replace. Maybe the HEPA filter would last the whole mission. It's very important that this is not just a separation solution, but also a collection, provides for the collection and safe removal. So we'd like to see some method by which how can carbon be removed while the system's still operating, so we don't have to shut down the process. We're thinking that removal could happen approximately once a week. We'd like the whole system to be operable for a mission as long as 500 days, which is a Mars class length of a mission. And we would like, provided with the challenge, some rationale as to what is the scientific basis for the solution you're providing. If there's any data that substantiates it, information like that. If you used modeling, that would be very useful for us to see. Next slide. So there, part of the specifications, we call out mass, volume, and power. Ultimately, for anything that we fly in space, we want to minimize the mass, minimize the volume, minimize the power. We put some estimates here for do not exceed. That doesn't mean that is the target we have. We are searching for solutions that are lightweight, low volume, and don't use a lot of power. So that's an important criteria for us. And the system would, depending whether it's in the gas phase or I mentioned it could be in the gas phase or the cold condenser side where this separation could occur. If it's in the condenser, again, we would need to look at something where we could separate, now we're separating particles from the fluid, the water, and how can that be done safely while the system is still operating as well. It's likely that the system would be running at subambient pressure from the cabin, if that makes a difference to your design. And I was going to say we are looking for solutions that either work in gravity or in microgravity, or are really agnostic to and would work in either type of application. Please make sure you specify that in the response. Next. So Natalie, I think this was not the updated one, so I didn't have the judging criteria in there, but you could move down to that if you would like.
There you go.
Yeah. So we're interested in feasibility, concepts of operation, which include how one operates this aspect of this will be a subcomponent of the Bosch reactor. So how does it operate? How is it started up? If carbon is removed, if some kind of replaceable filter is required, how that is done. We are looking at innovations of design. How is it integrated with the Bosch system? And then the quality and robustness of any supporting rationale or data that you can provide with it. So I think I kind of covered these a little bit here. The concept of operations is the ease of maintenance, ease of collection, removal of particulates, and the safety involved. Next slide. This, I talked about mass and volume, although these were specified, and also really part of this criteria, I think, although it's not really said, is power, but we need to make sure that we don't try to be on the high end of these. Although if it's a super duper efficient workable system and you're a little bit on the high end, I mean that might be still okay. And the last one, yeah, we are looking at innovative designs and approaches. We're not just looking for a filter. One of the issues of standard replaceable filters is that over time, if they have to be replaced every week over a 500-day mission, the mass will add up. And if the mass adds up, that's part of the replaceable mass of a filter housing or cartridge or paper, whatever it is. That can be quite heavy in the long run. So I don't know if, Chris, do you have, or you or Juan have any other things to add?
I think you've covered everything.
Yeah, Dan, in terms of that remark you just made about we don't just want a filter, I mean, it could be a filter that is able to regenerate itself, right? It could be a filter that provides long-term use and performance in a way that it can, clean itself when it gets loaded, or, just demonstrate long life.
Yeah. We do realize that with accumulation of carbon here, if we're talking about up to a kilogram a day, at a period of 5, 6, 7 days, you're going to get a sufficient accumulation that probably behooves us to swap out or at least remove that collected material on that kind of an interval, which would be kind of expected.
Wonderful. Is there anything else related to the slides that you wanted to say?
Yeah, the last one that you sort of hinted at, if you wanted to go to that, there are other technologies NASA is looking at that do produce particulate carbon. One is a methane pyrolysis system that breaks apart methane to derive and recycle the hydrogen, leaving solid carbon as a byproduct. Systems like that these potentially could be used for those technologies, but that's not the part of the challenge. This is just sort of an FYI. And I think that's it. Thank you.
Wonderful. Thank you, Dan. Thank you for that. I hope everyone found that helpful and learned a bit more about what this challenge is all about. So we'll move into the Q&A period now. And just a reminder, if you do have questions, to drop them in that Q&A box at the bottom of the Zoom screen. So we can start moving into questions. I've got a question from Stephen here, and Christine, Juan, and Dan, just whoever would like to take this, go ahead. Stephen says, if my information is correct, there is right now on the ISS a forward osmosis system. My question is, have you ever tried to condense the water from the Bosch reactor and pass it through the osmosis system?
I can answer a little bit there. So the implementation of Bosch in the spacecraft would be that we would take the water from the Bosch and expect that it would need to be cleaned up. So some type of water processing technology would be necessary. If we were to hydrolyze the water, it would not be done directly with the Bosch water. It would be done, so we would most likely run it through a water recovery system. So Station has a water recovery system that right now utilizes a multi-filtration beds and a catalytic oxidizer. There's a urine side, and that's a distillation, but we wouldn't run this through that distillation side. We do not have reverse osmosis currently in flight. It is a possibility. It is an alternative for a Mars mission or a lunar surface. It is possible that a new technology like that could be utilized, though we have not evaluated it yet, especially in this context.
Awesome, thank you. And Stephen also says, related to my previous question, what is the maximum flow rate of the osmosis filtration system?
That's really a question beyond, I think, this challenge. So, and I don't have that answer. I mean, certainly, what osmosis filtration systems can be sized to handle any level of water, from a small personal use to a whole city. So, yeah.
We have another question here. It says, should we include the mass of the water combined with the captured carbon / filter in the mass that a concept consumes? You
should only include any mass of water that you waste for some reason if your process causes it. We are recycling and collecting water, but you don't need to consider the mass of the water in your system. Yeah.
Okay. Can water escape the system when changing the filters?
Depends how you design your change out. Some concepts might have a filter, two filter systems in parallel, and while one is being used, the other one potentially can be used for a change out. When we're changing out filters, we're actually more worried about than water. If we're talking about the gas phase, is hydrogen and carbon monoxide that might be present in that gas phase. And so having some kind of a purge to purge those gases so they're not released into the crew cabin is desirable.
Yeah, and I think what they're trying to get at is, as they try to change the filter with any water, could any water escape, any minimal amount of water escape? And I guess the answer would be to not have any water escape or minimize it as much as possible. Correct, Dan?
Sure. Yeah. Especially we're talking about the gas phase side here.
Yeah.
Now, if they're talking about some kind of a collection means with water, ultimately, water might be able to be drained from the carbon if you're on the condenser side. In a spacecraft, typically, if we do have materials that are not dangerous, we can, like things like wipes and clothing that's wet and things like that, we let them air dry in the cabin to recover that water before we do something with it. So we would probably try to have a means to dry out the carbon or you that's part of your system if it was on the water side.
But bottom line, we want to minimize any loss of water.
Yeah.
Thank you. So this is one of the questions that we received before the webinar. My question is related to the water recovery system. How long is it in use? How long does it take to maintain? And what is the finest particle it can take in the circulatory system?
The current water recovery system in flight recovers water vapor, condenses water vapor with a condensing heat exchanger, but the gases that flow across that go through a HEPA filter. And Juan, you could correct me, but I think a HEPA filter standard is it removes 0.3 micron and above particulates. So there's a possibility that the current water recovery system may be getting some very fine particulates that pass through a HEPA filter, but nothing greater.
Yeah, essentially HEPA filter, when it's rated at 99.97% efficiency, that means particles are getting through at that efficiency around the 0.3 micron range. But typically they collect particles smaller and larger than that range.
Wonderful, thank you. And I just wanted to mention as well, I see a couple questions in the chat in the Q&A that are asking some specifics about the system. So if there is anything that we don't have an answer to today that we've got to go back and reference, we can follow up when we post the recording. The next question is, does the carbon particle loading change based on the time of day, or does it remain almost constant?
So I also noticed that VJ also had a question before that on flow rates. Did you see that too?
Yeah.
So the amount of carbon dioxide that is available does tend to change, or at least produced by the crew, does generally change whether they're sleeping or exercising. But the cabin atmosphere is essentially a giant sort of tank which has all that CO2 in it. And so nominally the CO2 removal system is plugging away as needed to reduce the concentration. But it can be, there can be a little bit more CO2 produced during the day than at night when the crew's sleeping. So there could be some slight changes.
The next question also from VJ is, you mentioned about typical flow rates of 20 to 50 liters per minute. What are the duct diameters at the exit of the hot reactor and at the inlet to the condenser to get a sense of the local velocity?
So we've only done sort of low fidelity units so far, and we varied the diameter of the gases. I would say that if a velocity is of interest, a particular, you can in your system you can vary the diameter of that duct. So really what we provide, if you want to make an assumption, it could be, our system could either be a couple inches or 6 inches diameter, I'm not sure, at the top of the reactor, but then the flow might be even as low as I'm going to use English units, but maybe, I don't know, a quarter, half-inch tube for just the flow, gas flow. But your system, if you need to have a velocity change to make your system work, you can manipulate the diameter as because you're going to interface with our system. So you can just specify what you assume our system to be if you need to look at develop an interface, but it's okay for you to change that diameter to meet the need.
Wonderful. Is the system in a gravity field?
Well, that kind of depends on where the system's going to be. If it's going to be on a transit habitat or something that's in orbit, then there's not going to be a gravity field. If it's on a surface, it's going to have a gravity field related to that particular surface. So if the moon or Mars, it would be those gravities for those planets.
And your solution could be for either partial gravity, such as moon or Mars surface, or no gravity, such as an orbital spacecraft, or it could be agnostic and work in both environments. Just specify which you're designing for.
Thank you. Do you have a preferred gap between the input and output pipes, such as 1 meter, that this should fit into? So do you have a preferred gap between the input and output pipes that this should fit into?
Yeah, I don't know if you can specify something more than that. You're saying, but I don't really understand the question. Is this how large your system is?
Okay, we'll move on to the next one. I'll give,
Yeah.
Jeffrey says yes.
Well, we did specify at least volume. There was a question, I think, also that came up maybe in the forum which is like, what length could the system be? For example, if you're trying to fit into a certain volume, but a volume could be, you could have something very long and very narrow to fit the same volume. But again, I'm going to give you English units, but we don't know what a Mars spacecraft, for example, or a lunar lander or lunar habitat, what kind of rack or design will be. It probably won't be like space station. Space station racks that hold equipment are fairly wide. But one concept that we've had is these called a pallet for an exploration system, and the outer diameter or outer dimensions are about 24 inches by 24 inches by about 6 feet. Not that your system would have to accommodate that, but that's just a rule of thumb of something that NASA's looked at. So I would say don't try to make these any longer than 6 feet, but certainly shorter the better, I think. But if your system for some reason needs some level of height, try not to at least exceed that amount.
Wonderful. Any preference for aluminum versus stainless versus other materials? And does the material cost matter?
I think for materials, the major concern would be the mass. So, if you can use aluminum, you'd have to, of course, look at the constituents that you're flowing through those, that material, but you'd want to go with a lighter one. As far as the cost matter, if aluminum is, let's say aluminum is very light and it's more expensive than stainless steel, you'll probably the cost probably won't matter as much as being able to reduce your mass.
So one thing we are looking at here are concepts and low technology kinds of systems. At this point, once NASA gets its ideas and perfects the flight hardware, NASA will probably choose its materials to use, what could be some advanced alloys, titanium, things like that. So I don't know that the material that you're choosing right now is that important, unless it is key to say what drives your mass. So I think what Chris said was just take that into account. Yeah, you could choose a lighter weight material, even though it's expensive, but compared to what things cost for spaceflight, may not be big in that perspective, or important in that perspective.
Awesome. And they followed up and asked if titanium was okay, but based on your answer, it sounds like it is then, Dan.
Yeah.
What kind of pressure drops for the particle removal device can the system handle?
That's a good question. Juan, I don't know if you can field that, but what typically is used for NASA systems, we do want to maintain the flow, and it really will drive the pump we use, a recirculation pump, I think. But
yeah, I don't know if I have a clear answer to that. The only reference I have is the other system that you mentioned was a Sabatier, and then there's a plasma pyrolysis assembly. So with that, we're working towards developing a filter for that system, or a carbon capture system. And I think we were allowed pressure drops. We had pretty good pressure drop allowance. I think, if I recall, I think they were of the order of maybe up to 10 inches of water. I can't recall exactly, but it was a pretty good pressure drop allowance that they provided us. So, but if you want a more specific answer, we'll have to get back to you on that. As far as the Bosch, I don't know if that also holds for the Bosch, Dan. So I may be giving something that's not a good reference, but.
I think in terms of what we were doing before, I'd have to see what we considered to be a pressure drop that sort of killed the system. But I think we were able to accommodate a few PSI drop, I think. But but it can't be too much because we're trying to operate the system at a somewhat a negative pressure, and if there's a portion of the system that has to go positive, then there's possibility that leakage of hydrogen can get into the cabin. So you know, keeping the pressure drop low is pretty key.
Thank you. And then we've had someone ask what the maximum mass of the system can be. That'll be 60 kilograms, but as Dan mentioned earlier, you should be aiming to minimize that as much as possible. That's the maximum that we're interested in, but you'll basically score higher points throughout the judging criteria if you are able to minimize the mass. Is there anything else to add there?
I think you hit it on the head.
Yeah, I think you got it. Yeah.
Awesome. And then Teamer has asked, are you planning to publish the recording of this webinar? Yes, this will be on the challenge page. It'll be in the update section. It might take just a couple of days to get the recording up, but we should have that up by the end of the week. So you'll be able to watch this back. And then he also asks, if I suggest a scheme which contains the same elements as the original NASA schemes, example, the pumps and tubes and filters, should I specify their parameters, or is it enough to say that they could be the same as in the original NASA scheme?
Only if your requirement is that they're different than the NASA system. So.
Okay. Wonderful. And there's another question that was asked ahead of time. It says, in addition to carbon, does the series Bosch reaction vapor output contain any other contaminants from the catalyst that we should be concerned with? And is the water from the condenser only used for electrolysis? I pronounced this wrong to you guys the other day, but electrolysis, or will some be routed to the WRS/ECLS modules?
So it's likely that 100% of the water will go through the water recovery system. Even if it's electrolyzed, it will need to be cleaned up for that. Was mentioned, what other kinds of contaminants? Well, since it's not a complete reaction, but also because there will be some byproducts, there's a possibility that there'll be carbon monoxide, unspent carbon dioxide, unspent hydrogen, water, maybe some methane, in addition to the solid fraction that may be present.
There may be some tiny bits of catalyst mixed in with the carbon because the process breaks that catalyst down and the carbon attaches to it. So you may find some very, very fine catalyst particles in there as well.
Wonderful. What level of technology readiness is NASA expecting in submissions?
That's a good question. I mean, certainly it's a 3 to 4. Technology readiness 3, which is proof of concept. You're giving us concepts. You don't necessarily have the money to build something to evaluate them, which you get into the proof of concept. We'd like concepts. There's enough supporting information, if possible, that you can justify that your concept works. So either you have built something and you can demonstrate that it works, or you have some kind of supporting data, including if it's test data or modeling data or something else would be valuable.
Great, thank you. And I did have a kind of a similar question, well, related to that asks what kind of attachments can you upload? Because there is the option to upload some attachments to the submission. And related to what Dan said, you could upload anything that helps prove your concept works in that section, but you can also just link to those throughout the submission. So the judges will likely not read every single, the full web page of anything you link, but it is helpful just to link back to any proof or any information that will help support your submission. Why is NASA interested in this alternate way to maintain a breathable atmosphere in a spacecraft? Why not continue with current methods that are being used?
As I mentioned earlier, the Sabatier, which is the sort of the state of the art, can only recover half of the carbon dioxide because there's not enough hydrogen available in flight, because that's a very inefficient reaction. And so we're trying to go beyond approximately 50% recovery of oxygen to close to 100% recovery.
Wonderful. Is NASA interested in working with winners after the close of this challenge to further investigate and test ideas?
I guess it depends on the quality and how successful the responses are. I think if there's something that is quite good and we need in more information, we would be interested in making contact.
Wonderful. Can relevant research papers about similar technologies be a valid data as backing for the proof of concept? And should we provide DOI and links to those studies?
What's DOI?
I'm not sure, Ross. Could you clarify what DOI is? Just give them a moment.
But I mean, that is some of the kind of data that I think would be useful.
Awesome. And in general, if there's anything that you have links to provide further support, those are always going to be beneficial to see. So if you have access to studies or anything as proof, do provide those links if you have them. And Ross, if you can clarify what DOI is, I'll just give you a chance to do so. Does NASA have a preference to where or when the carbon particulates are collected within the system?
Yeah, I think we would like to see them collected prior to the condensing heat exchanger. But if not, there would have to be some kind of collection afterwards. We need to, remove those particles before they go further downstream.
I think we've always thought that the removal at the gas phase is most desirable. But it occurred to us that if some new novel method for separation with water was available, that would be something that we would consider.
Okay. And Ross just clarified that DOI is a digital object identifier, so it's a shortened link for research papers or publications. Yeah, I think that the same
a link would be better, or title and authorship and journal would be best, probably.
But,
I don't know what to do with the DOI, so yeah.
Yeah, if that's all you have, you can still include that. But yeah, as Dan said, if there's something, if you've got the name of the paper or author or link, that's preferred. Is NASA expecting any kind of drawing with the submission, or drawing or anything similar to that?
It's highly desirable for us to see what you're planning. Highly desirable.
Wonderful. Are some materials that are prohibited to be launched in space other than the obvious flammable materials? In terms of including those materials?
Well, actually, there are very, very, very flammable materials that are launched to space, like the reaction control engines, things like that. Just as long as things are highly protected, there are prohibitions on nuclear materials for sure. There are concerns about certain batteries without being tested, but I'm not a materials expert in this case. I don't know, Juan or Chris, if you can add anything, but it's probably could be a fairly long list, but I don't know.
Yeah,
I don't know either.
Yeah, I'm in the process of there is a materials database that NASA holds for supporting contractors. And I'm going to try to find that link and paste it here, or I'll send it to Natalie later. But if I do find it quickly, I'll paste it.
Good. And if there is any specific, as you're going through and perfecting your idea, if there's anything that comes up that you have concerns about in terms of specific materials, feel free to paste that in the forum as a follow-up as well.
So
Okay,
Natalie,
that-
there was a question I think that you had asked us before, which had to do with, well, what have we tried already, right? Because obviously we didn't just have only a sort of a frit filter there. So we had considered, could we just have a replaceable sort of a HEPA filter in line, but we realized that over time, having to replace the filter over repeatedly with new and new, we'd have to bring up a lot of massive filters, which was fairly prohibitive. The second thing was we tried a frit filter in which we sort of scraped off the carbon cake from it over, but we found that maybe the scraping caused carbon to be pushed into the pores, but we basically clogged up the frit filter from that. We have tried a combination of a frit filter with a cyclone type filter. One of the issues with the cyclone is that they're generally not near 100% efficient, but also being that we're in a humid atmosphere, the properties of the carbon particulates change, and we didn't quite get maybe the cyclone action as we expected either. So we had trouble with getting perfecting that type of process, and that only works in partial gravity.
Thank you.
And the other thing is that we don't really understand how the particles are behaving in the flow. The particles could be sticking. They could have, they could have a myriad of different properties, whether they're sticking to surfaces or collecting in areas, outside, going outside the flow. Those are things we really don't understand right now. So, those are additional challenges.
Thank you. And Juan, I see that you also pasted that NASA material database link there for anyone that needs it. Just go to the chat and that link is shared, and I will also share it on when we share this recording. So that is all the questions we've received today. If you do have any really quick last minute ones, we have 2 minutes left, but otherwise, if you have follow-up questions or you feel that any of your questions weren't properly answered or there's still outstanding things you need to know, just feel free to paste those questions in the forum as always, and we'll stay on top of that. There might be a short delay over the holiday period in getting to those questions, so if you can, the earlier you can post them, the better. And then of course, after the holiday period, we'll still be back before the deadline on January 12th. So thank you so much for tuning in today. We're really, really looking forward to seeing everyone's submissions and see what everyone comes up with. Dan, Juan, Christine, do you have anything else to note before we log off?
I just want to say thank you for all of you that attended, and I hope that this becomes a very successful challenge.
Likewise. Wonderful. Thanks again, everyone. Have a wonderful day.